carry names which I don't know. The ones from the Bible I looked for them. The one vernacular one I looked for. No one told me the reasons, but I guessed maybe it's because of ABCD. You can't carry a name which you don't know how it comes about. It's not proper. That's full chalk written on that place. Haji. How are you? You don't want to be Haji, you fear going around the Kaaba. It's already time. Yeah, that's why I start. Not going to wait for my mother to go. Oh Lord, do they still say that? Or you don't know Karamocha?
They still say so.
They still say so. I don't know how true it is. I don't know how true it is. Yesterday when I was opening my notes, I realized that we have covered too much for even 2 tests. Why are you pointing about electricity? They cannot allow my lecture which goes late to operate without electricity. I'll sack them.
You are a shareholder.
Yes, as a shareholder, I would sack them. Spend a week without food. Only comes when my lecture is there.
You mean it's soon going off, so that has worked.
It's not going to go DJ. Dose. Now it does also. Okay, good afternoon. So yesterday we were able to come up with after some altercations solving the differential equations that we had come up with, as we separated the variables, we came up with a solution, and got, for example, the potential being the same as the potential at the x-axis, the y-axis being the same as the V naught. That was at the electrode that was terminating the 2 grounded electrodes, which was equal to the summation of from the field 1 to infinity, the coefficient Cn, then sin n pi over V, 1. And we said with this kind of expression, we can take advantage of the Fourier series, and then find these the Cn's. So that would be able to help us find the coefficients in our equation. Then once we know the coefficients, we find the so in your compute, how do you call the course? Computer what?
Computational physics.
Computational physics. In your computer programming in physics, because you can't change the name. curriculum says computer programming in physics. So in your computer programming in physics, you can go ahead and try to plot this using Marvel, and then see how it looks like, and gives you an idea of how these field lines eventually are forming up. That is your business. So using a technique devised by a 140, using a technique devised by Fully, whom you call Fourier. We multiply both sides by a factor. We multiply both sides by a factor sin p pi over b. Sin p pi over b y. Where p is an integer, and then we integrate from y equal to 0 to y equal to b. So this was our system. This was x, this was y, this was our z, and then we got the 2 electrodes, which are semi-flat. Terminated by another electrode, and this was at B, sorry, A, B, this is at B naught, origin O, grounded, and grounded. So we introduce the factor P, the factor sin p pi of B, y, and then integrate from 0 to B, that is integrate from here and cover the whole space between the electrodes. So from 0 to B, we do the integration of our Fourier series. So equation 8, which is this one, which we got yesterday, becomes equation 8 becomes, so on the left we got V naught, but we are multiplying by the sin p pi over by and integrating from 0 to b. So this would be V naught sin p pi over by. Since we are integrating from, this would be along the y, I mean with respect to y. The right hand side would be the same as the summation from n equal to 1 to infinity, integrate from 0 to b, and then we have a sin pi b over n, and then is it pi b or n pi? N pi over b, and I change it to. Some people just look for danger. You always together electric. What products are you exchanging outside? Huh? The what? You are submitting the assignment. N pi over b y, and then we multiply by this here, sine p pi y, and then y. The rest is algebraic gymnastics. The rest is up to do the integral. I don't know how to integrate. That's your business. So the left-hand side of equation 9, this one here is equation 9, Ix. This was 8. So the left-hand side of equation 9, the left-hand side of equation 9 gives, so the left-hand side is integral 0 to b, b naught sine p pi over by dy. When we integrate this one, what we get? We get what we differentiate this, which would be minus cos p has to, so there would have been 1 over p, so it would be p. So then, sorry, b, this b, as it is down, then p will be down. So it will be the same as minus for the gas, so minus b naught. So we have b p pi down, so it will be b over p pi, and then cosine of p pi over by, and we put the limits which are from 0 to b. I don't know why the limits are missing on my notes. You substitute b, it becomes cos pi, and cos p pi, and then you put in 0. Cos 0 is 1, so this would be the same as minus b naught. Put a b here, they go, so it is cos p pi, so it will be b naught b over the p pi, and then you have the cos, so this would remain with the cos p pi minus 1. So this is cos p pi minus the 0 in comes 1. And from your beautiful mathematics, this can be equal to 2b b naught over p pi if you have p being odd. If p is odd, and then everything would be 0 if you have p is even. If you have cos pi is negative. Cos pi is negative 1. I'm putting in stuff. I'm putting in odd numbers. So if you put 1 as an odd number for starters, that would be cos pi. which is minus 1, minus 1, minus 2 times negative out, positive 2, which is why we got a 2. So when you put 3, so cos 1 pi, 3 pi, 5 pi gives you minus 1, minus 1, minus 1. And eventually we do this. Then when you put in the 2, 4, 6, 8, blah, blah, it becomes cos 2 pi. Is the 1. 1 minus 1. So all those will give you 0. So using equation 10, which is, I think, this one which we have just put here, this is equation 10, x. This is, Isaac, you see, this is not my business, this is your business. This is your business, this is mathematics. There is nothing physics here. Ask your question, I'll just keep it. Ask your question.
Like, sin p pi d outside bracket and put y, is it the same as sin p pi y over d?
Who has understood the question? I'm not laughing at you, I just want to understand the question.
She's asking, for example, where we have b cosine of p pi over b bracket, then the y. If someone put the y inside the bracket, it would be different.
Who can answer for me? Yes.
P pi over b is considered as a constant. It's like having cos 2y.
Okay, I'm just looking for, if I put my vest, I have a vest inside. Do you normally see it? If I put it on top of my shirt, what happens? Eh? If you, it depends on how you want to look at what has happened. If you wanted to value the clothes I'm putting on, would have the value change? Now, if you wanted to consider me whether I'm sober or crazy, how would you rate me? My vest is on top of my shirt. Not a vest that it is a vest sweater, but my vest which is inside now. This is what it is. If I put it on top, or if my underwear was on top of my trousers. If it is evaluating Isaac, listen, if you were to evaluate my faculty, my top faculty here, and I come here with my underwear on top of the, even if it is fitting well, then you look at me and you are like, what the hell is going on? My underwear should be inside. Well, you may start dressing like that because of me, but that is not that's not how I should be dressing. So the idea is that we are integrated with respect to y, and y is the variable that is taken. So our integral cannot be you cannot have this one now mixed inside here when actually these are the constants. Then you put what you are integrating with respect to. But it doesn't hurt even if I put y here. If it is about seeing me dressed with the value that I want to carry around, but then I would look strange when I come here like that. So the way to write the equation is that, Moise said, these are constants here, so they should be in the bracket, or whatever, whichever way you want to write them, as long as the variable that they are varying with, because this is the variation of y as a constant, and then with these constants showing you how the amplitude will be either higher or lower. Okay, so we got the left-hand side. We have the left-hand side. But remember, we had the right-hand side. And the right-hand side was the Cn. Just want to be sure. The right-hand side was the no, the left-hand side was the sine p pi, which we have finished. And the right-hand side was the coefficient Cn sine n pi over by sine p pi over b y. So with this, it means that using the two equations, that is equation, I think we have just done equation, this is 10. So the right-hand side, we finished the left-hand side. The right-hand side of equation was equation 9. Of equation 9. Of equation Ix, which is 9, becomes equation 9 is, we are integrating from 0 to b, the coefficient Cn sin n pi over b y, and we multiplied it by sin p pi over by. We are integrating with respect to y, and once you do your mathematics, this culminates in 0 if p is never equal to the n, and Cn b over 2 if p equals to n. And this one, call this one equation 11 x I. Now that we got the left-hand side and the right-hand side, ideally, then we can say that using equation 10 and 11, using equations 10 and 11, and we take the case which gives us themes. P, we could only get stuff when P was odd. And on this one, we are getting a value when P equal to n. So this is the only condition that gives us something. When P equal to n, and when P is odd. So then, so for P equal to n and odd, then we have the 2BV naught over the n pi, which is p pi, equals to this one here, CNB over 2, and then we can find the CNs now. So this implies that Cn, so the 2's, sorry, the 4, the b's go, it's only the b's which go. So this implies that C naught, sorry, Cn is equal to 4V naught over the n pi. Thus, these coefficients will be equal to 4V naught over n pi, and the condition was if n equals to p, but p, remember, we just got it as an integer, but n we know it. N is the number of field lines. So we are good to go with n. That is, if n is odd, and everything else will give us a 0. So, and it is 0 if n is even. Hence, we've gotten the potential in between these two electrodes, Vx being the same as the Cn, which is 4V naught over n pi. Then we are summing up from n equal to 1 to infinity, 1 over n sine n pi b, sorry, n pi over b n pi over b then y exponential minus n pi over b x. This is our potential in between these electrodes at a distance a along x and at a distance b along the y, with the terminating electrode being at a potential v naught, and of course having no variation of the when we have taken the potential along z to be constant, yes. Then and outside. This end here. You mean it should be here? It is this. Okay, let me first check whether. Yes, you are right. It is. There is no end here. There is no end here. Kasada. Kasada. Do you do the turn like I do, or it's normal? Is it kasada or kasada? The Baganda, those ladies who are saying kasaja, the Baganda say kasaja katono. So those who are saying kasaja, you say it properly with caution. So there are a bunch of these examples in graphs which you can go chop and be able to be acquainted with these expressions. So we go to our next section. We'll finish the Cartesian coordinates and see how we can use Laplacians. The other time we were just getting a simple case, and then we were only taking one variable. We looked at the general case. We just learned how to separate variables. We've just taken the case of the rectangular coordinates or Cartesian coordinates, and we have managed to find out, but still here we eliminated the z part by choosing the example that does not involve the z part. So you go to graphs and chop the rest of the stuff you want to get acquainted with. So 2 is the solution of Laplace's equation. Solution of Laplace's equation in spherical coordinates. In spherical coordinates. Spherical coordinates, but still separating the variables by separation of of variables. So we take our sphere, and you remember that our sphere was having the coordinates varying in this form. You got a sphere, and then you got the equator here. So we can have the zenith here, and then we have you can have your y here, or have the x here, have the y here, and then at any one point on the sphere, you can have this point from the center being the radius r, and the more you blow the guts in the sphere to bulge it, if you are having the balloon like this small and you put a mark here, it may look like, or even if you put the mark exactly at the zenith, once you start blowing it up, the mark starts going this way. As it becomes larger, the mark keeps moving away from the zenith where it was. And then it keeps subtending. It keeps making this angle theta. Whereas when you sweep across the equator, this one here, along this plane here, which I'm calling the equator, this plane which is having the axes, the zenith, the x, the y, yeah, the y, the x, then the zenith, then that angle, this, if you just cut a slice piece of this sphere, this plane here, of this slice, would go through an angle here, which we call the azimuth. So R is the radius, and once we separate the variables, it gives us the radio equation. So this is the radio, it culminates into radio equation because of the radius. Then this angle subtended, this angle here, the zenith angle, which is being subtended as the sphere becomes large, that angle theta, we can call it zenith angle. It eventually gives us an angular equation. We shall deal with these two. But the phi is called the azimuth. Azimuth. This azimuth, for this case, we shall take the belly of the sphere to be an equipoential surface, so that it does not affect our equation. So we shall talk of what we call, we shall use what we call the azimuthal symmetry. So once we use the azimuthal symmetry, we remain with the two variables. Radius for the radio equation, and then the theta, the angle theta, the zenith angle, to give us the angular equation. And then we do the algebraic gymnastics. However, we start from the beginning that the Laplacian in spherical coordinates where we are already, Laplace's equation is, so we have grad squared V is equal to 1 over R squared, Kali by Kali R squared Kali V by Kali R, plus 1 over R squared sin theta, Kali by Kali theta, sin theta, Kali by Kali, Kali V by Kali theta, and then plus 1 over R squared, sin squared theta, Kali squared V by Kali phi squared. And this should be equal to 0 from grad squared be equal to. Please, in your free time, confirm that the Laplacian grad squared v equals to the divergence of the gradient operator, and see whether you take this using definitions of the gradient operator as well as the gradient of the, of course, using the gradient operator in either Cartesian or spherical or cylindrical, and see whether it will give you these things. But you don't need to cram these things. I'll give them to you in a test or exam. But if you know how they came about, you'll be even better. You don't even look for them. So in this case, we assume azimuthal symmetry, just to make our life easier, so that our potential varies varies with only the radius and the angle. Azimuthal, for those of you who were not there during the course outline, it means that the azimuthal symmetry here, we are saying that we are trying to avoid the variables will be independent of the phi in spherical coordinates. There is a phi in cylindrical coordinates, so you can't just say phi. So what is left is all this minus this part. Once we have neglected that. So what happens is like in your academics, when you come here and you want to pass, you first put relationships aside. And then you go to the library. So that's what we are doing. We are having azimuthal symmetry so that our life at campus is independent of the relationships. And then separate variables. Make sure we attend all lectures, make sure we go to the library. So then we got this one surviving, so if we multiply by r squared throughout, we survive by the 2, so we remain with the Kali by Kali r inu r squared Kali v by Kali r plus 1 over r squared sin theta Kali by Kali theta inu sin theta Kali v by, and this equals to, I've multiplied by r squared throughout, and so I've skipped that step to not to waste my time. So under this part, let's say this is our beginning equation. So separation by separation of variables, we let the potential, PR theta to be a product of the two, yes.
As if that r squared, this is supposed to disappear.
Yes, it is supposed to disappear, thank you. was excited to write many things. Why don't you ask me instead of murmuring around? Or tell me, it is after I had expressed interest in the mamas I'm hearing that now you had to ask. This is supposed to be just one of us. Yes. But had you written it? Had you written it properly or as I wrote it?
I'm this side of late. I've already written everything.
You had already written everything. So start being smart. I think that makes you, that answers you.
But next I will correct you.
Good, I'll be glad. So so this will be a product of these two solutions, the way we have the capital X and capital Y and capital. So today you are going to see the capital theta and know how to write it. So this will be equal to the product of the capital R, and then the capital theta, you write this O and put an H here. And then small theta. In the notes, in the books, it is an O with some nicely done stuff inside, but just put an H, a capital H inside. And O, then it will be capital theta. And then the other one will be just a dash, an O with a dash for small theta. So today you have known that there is a capital theta. DJ, did you know there is a capital theta? But you know there is a small omega and a capital omega?
Yes.
Yes, because of angular momentum. So we now have this as our solution, and this will be our equation 2, and this is the radio. This will be the radio component of our solution, and this will be the angular component. So substituting in the equation 2 in 1, substituting equation 2 in 1, this equation here in 1 yields, and of course divided by this one here, and dividing just like we did for the Cartesian, dividing by V our theta, which is equal to this, we get, I'm not going to make any mistakes so that Fred doesn't get what correct.
I will get in electronics.
Even there, I'll make sure I don't make none. I don't make them intentionally. Sometimes I feel like I can make sure things go without seeing. That's why I keep these notes on, because I don't want to give you chemical when everything is okay. And if it is like Fred who just writes whatever I put. So substitute. If we substitute for R whatever here, the theta would be a constant. And then we have the dr. And which R do we have? This small. And then here would be the theta is already outside, so this would be capital R, small r. We come here, R becomes a constant. Keeping R as a constant and the partial differentiate with theta. So this would be the theta sine the capital theta, the small theta. And then we have two equations. Then since they are equal to 0, we can equate each of the equations to a constant such that when we add them up, they give you 0. So this would be that 1 over R, after doing whatever you are doing, which you do in your free time as a revision, ddr into R squared, the capital R, the small r, plus 1 over capital theta, sine theta, dd theta, small, into sine theta, the capital theta, by small theta, will equal to 0, and this is our equation 3. From choosing a constant for our own selfishness, then we get that this radial equation here, we have separated everything here is about R, everything here is about theta. And so this is the radial part, this is the angular part. From 1 over R capital, the small r, into R squared, the capital R, ddr, equaling to, so we can say, do we say from or we let? We let. So let this equal to some constant L into L plus 1. So we call this one, well, these two will be equation. So the angular equation, 1 over capital theta, sine theta, d theta, into sine theta, the capital theta, the small theta. So what will this equal to? Minus L into L plus 1. So this would be equal to minus L into L plus 1. And then we can call these two equations our number 4. L into L plus 1 is a constant that we chose for our selfish reasons, we shall see later. It is some k, and the other will be minus k. So L into L plus 1 is just a convenient way of writing the separation. It's just a convenient way of writing the separation constant. Just a convenient way. Instead of saying k minus k, we just put those arrows for purposes of getting what we want to get soon. I thought you had gone so that I give my attendance and take you as missed.
That's my expression of continuous.
Sure, give us. As long as the letters you put in will be having a meaning, like our L will be having a meaning soon. Guys, you must try to understand these things so that you become free with them. Like be at peace with them. That's why when I was teaching electricity and magnetism, I was saying they can't just go in Paris, then agree that the current will be flowing in this direction and say that's the conventional direction. They should give an explanation why. So you don't just say, and here they said this, I'm not that type. What I can't explain, and I don't bother. Yes, please.
Why they don't always don't always let it to be a constant?
What?
Don't always let it to be a constant. They choose A, okay, C.
Why don't they choose what? P?
Oh.
O. O, because you can confuse it with 0. So which of these ones is O? It is until sometimes some people have to be forced to do like this to make sure that that is a 0, especially if you are trying to write things that are concerning digital stuff. You are forced to put in, if you are having a 0 and O, you are forced to put in a 0, a slice, to make sure that that is the 0. And it is sometimes it is not easy to find a UBO. Have they put is there a number plate now which is UBO? Have you seen UBO? Because there is OPQR, right? Before they bring you, but have you seen a UBO? Because now we are on UBR. You have a series of UBO. That's right. Those are the things you should be concerned about. Even I think UBI or UAI was not, I don't remember, they are like, because it was confusing for an I, but I think I saw some I somewhere. But you can't find the UBO. You don't have cars. But even if I have a car, I can't own all the number plates. You have? You have a good order. So it's a nomenclature problem. That if you use it, like when I am giving my Yahoo email to people, I write it in capital, and some people say, "Is it in capital?" Even those who are IT compliant, they know an email is not case sensitive, but then they're asking, "Is that in capital?" This is my email in the Yahoo one. So when I give it to this and I say this is yahoo.com, and then they're like, "But is that in capital?" But if I had written it like this, what questions would I get? Many. Is that a W or U? Then is that is an N or H? A lot of questions. So, but if it is the capital, it is very elaborative. You get the point? Okay, back to my business. We've chosen this convenient constant, and once we have chosen it, then we say that the radio equation, after we have chosen, we've let the radio equation, we've let that equal to that equal to that. So now the radio equation, you still be able to look here. I'm too economical with the board. The radio equation, the equation of the radius part, the radio equation, we multiply by r at both sides, so we remain with DDR, in r squared, the capital R and the small r, would equal to L nu L plus 1 times the capital R. We are at equation 4, this becomes equation 5. Here. Sorry. You say you wrote radio instead of radio. This is radio, not radio. Not a radio set, but radio. And he wrote a radio. Fred, you have written a radio. I gave you an opportunity to see radio, you couldn't. That's why I keep on script. The moment I go off the script, then I write my own things. That's where my problem is. My experience is that if I am to do freestyle, I should be having these notes projected like on a projector.
Yes,
then do freestyle. But if I am to give you the thing that you are writing, and then I go freestyle, we shall be in problem. Because some of you here are here to say, let me just jot down and go, God knows. Jeremy, where were you yesterday? You attended. Jeremy, you attended. No, there was no power. Because I have an attendance list here. And when I didn't see you, and he had no Wi-Fi to come, so he uses a ticket that uses Wi-Fi. Or you assume that since there is no power, there is no teaching. I'm just kidding. I just wanted to show you that I've seen you, that you are around. Has general solution, this radio equation, you should be happy that I'm one person who knows all of you. It's not about few. Even when I used to teach 200, I would say each and everybody's name. So, Thomas, you go to my videos. Everybody, I knew their name. So this equation here has a solution, has a general solution. Those of you who know mathematics will be able to help me. Has a general solution. As a general solution of the form so the solution will be the RR, remember, which we multiply with the theta to give you the V, and this is given by the AL, R to the L plus BL over R to the L plus 1. And this will be our equation 6. This is the general solution. You, those of you who do mathematics, you can help me understand how. So this is our selfish constant that we chose. And L is the order of the polynomial that we shall get soon. Yes.
What is it that in the derivation of this chemical that we are getting, we're in that eliminating algorithm, flow symmetry, that amplify? What is it that we need to come?
We are trying to come to senses by first doing the simple things first. We first eliminated phi and theta and only worked with R. Then we understood how we can get the constants using the boundary conditions. Now in this case of spherical symmetry, we are saying fine, we can start with an example, and in this case we take a case whereby at the around where the angle is supposed to be changing, we take the potential to be constant. And if the potential, if you got I did come with my demo, but if you get a ball around its equator, if you took those points to be having the same potential, then we can forget about the azimuthal part, the one over phi. Then we do separate variables first. In the future, if we can get a configuration where the azimuthal symmetry is not corresponding to the constant potential, is not a then we put it in. Just like in electricity and magnetism, when we were looking at the we had our charges which were moving along the x and y. So we first got it as a circle, and we got the center of the circle and the coordinates, the radius of the circle and the points at the circle. Then that's when eventually we assumed that, not assumed, but now we introduced what if there is the z, the vz. Then we got the spiral thing going up. Now here, we are taking a case of if the sphere, if our sphere had a constant potential, which is the case anyway. If you got a charge, if our sphere is a configuration of the electric field produced by, for example, charge distribution, but let's take a point charge being the source of the field lines. And then we take a sphere enclosing all this all over. Then if you took this part here, this field line is the same as this field line, the same as this field line here, same as this field line, this other field line, this other field line. So around the azimuth, all the field lines there are having the same properties. And because you are going around the radius of the sphere, potential is given by V is equal to 1/4 pi epsilon naught 1/r, where r is this radius here, which is the same. So they all have the same potential. So that part is an equipotential surface. So why the hell would we be concerned about its potential when we know the potential is the same around that place? So we remain with just the radius and then the effect of the radius as it becomes larger on other places other than the azimuth, and then the angle at which that radius would be alternating as you move far away. Remember, I'm just talking of blowing a balloon, but in a sense we are looking at when we are taking the spherical surface becoming larger because we are moving away from the center. As we shall see in one of the examples, we are moving away from the center. So if we are moving away from the center, our sphere is bulging. But it is not that we are talking about blowing gas in a sphere and then it's in a balloon and then it's bulging. No, we are looking at different points. Remember, eventually once we are producing electric field and we are doing radiation to do our communication, we are looking at how far our communication can go using the electric field that we are trying to send out. That's the essence. And once we got to know that, then we say, yeah, we can send our signals as far as we wish, since we know how they vary. Okay, so the angular equation, our radio equation gave us this solution. So the angular equation here, has the form. So the angular equation here, we multiply by theta, both sides, capital theta, so we remain with 1 over sine theta, d theta, then sine theta, d theta, the capital theta, the small theta, and this would be equal to constant, which is minus L in L plus 1, and then multiplied by the capital theta, and this would be our equation 7. So from mathematics, we put x equal to cos theta, and if we put x equal to cos theta, then we get dx is equal to, if x is equal to cos theta, dx equals minus sine theta, sorry, cos, yes, sine theta, d theta. So, I know normally when I reach this point, people start wanting me to do their mathematics lessons. All we are doing is, I don't know, it's like lying a lady. I asked my lady friends that why do ladies want, I think I told you that before, that why do you always allow guys to lie to you? Like I can walk to a lady in town who, well, even if she doesn't know me, I tell her my parent is mine. I am waiting for the survey for the collections at the end of the month, and I will even take you out. And I can take you to Dubai, you spend a week there. And she knows Mapera is for the Catholic Church. But she accepts and says, so as long as I get the money, wherever I get it from, whether I have stolen it, whether I'm corrupt in the government, and then she will even go to Dubai happily. And even make me happy. So I said, what the hell is that? So they told me, we know they lie to us, but the only thing is that we see aspirations in them. We see that they are... I have a different interpretation. My interpretation is that they don't care whether you run, when you run broke, they get someone else. But this one convinced me that they know that you have aspirations of owning Mapera. You have dreams. You have a vision that can manifest at one point. I don't know whether she was lying to me, whether it is the truth. Me, I have a different meaning. My meaning is that she will run you broke, whether you have stolen, whether you have killed people for her. Once you are broke or they have imprisoned you, then she gets someone else. And it still remains that. You can go to hell. But she said this guy has a vision. He sees himself owning Mapera at one time. I don't know how you guys do it, if the ladies here, but that's what I was told. She had what? You are not liable. I didn't hear that, but I don't want to hear it. Let me continue. So they put X equal to that, the X equal to that. We are doing all this, we do all this with a vision. We know where we want to go. So we choose it properly. So you can't say, so don't plan and say, now when we reach here, we say put X equal to cos theta. And then the X equal to minus sin theta d theta. Just like we put the L in new L plus 1, soon we are going to see what L is all about. And then remember, oh, this is why we chose something like that. But of course, the second constant, we chose the minus L in new L plus, so that the addition of these two gives us. So if we have chosen P equal to X cos theta and the X equal to minus sin theta, already we are getting something close to what we want. We are having a theta here, we are having some sin theta here. So we have we put the, where there is cos, we can put there X, where there is a sin theta d theta, we can put there the X. But before then, that's for any function X, that's for any function X, which we say function Lx. Then we have from chain, is it called the chain rule? df d theta would be equal to df dx. I used to enjoy these things. Then dx d theta. I chose, I majored in physics. But before I majored in physics, I used to choke. It was nice. There is a book called K. Stroud, Engineering Mathematics. The man had solved everything. Even the exercising would go on and solve. So I had done all that stuff. So there is nothing like I do a number, then I'm disappointed that I haven't understood or gotten the answer. The answers were there. That goes to Isaac. Isaac, you are not spending time in your course. If you spend time in your course, you will enjoy your course. Do extra. I told you the story when we were watching a movie, since you are in third year and you are all adults, we were watching an adult movie when we were here. After reading, maybe 1 a.m. or 2 a.m. So no one even, you couldn't even hear like someone moving the leg. So one fool said, if we were concentrating like this in our lectures, we would all get first classes. It sank deep in my head. We were all very attentive, no talking. drunk or something. So out of nowhere, I said, if we are concentrating like this in lectures, we would get first class things. So you should really put some time in your. I enjoy my teaching because I put an extra time in my preparation to earn money with ease. My 2 hours end when I haven't felt anything. Like it's like like yesterday, my hours just went when I was still wanting to go home. And for you, you have even extra. You will get a good paper and get a job. Me, even if I come here and I just say, and you find this on well, I will get my salary. But I still go on and chop the numbers. So this is the product rule. This will go, we go back to the FD. But this helps us normally if we have the function of x also being having if fx is equal to x squared plus t what we can replace. I don't remember very well how it was going. So this would be the same as minus sine theta df dx. You don't ask me to go to your mathematics. And this would imply that the d theta would be the same as minus sine theta dx. This is our equation 8. Using equation 8 and equation 7, anyone having problems on how this came about, you consult your mathematics. So I'm going to substitute in this everything to do with d theta and then replace it with dx. Where there is d theta, I put minus sine theta dx. So I will not waste time. I'll say 1 over sine theta small, then times minus sine theta dx into sine theta times minus sine theta d capital theta dx will be equal to our second constant, which is minus L in nu, L plus 1, and then multiplied by the capital theta. Life now is becoming a little easier, and everything is reducing to something that looks sweet. This solution here I've just rubbed, you don't need to cram it. Even if I ask this question, or if this question is brought, normally this is given. Assume this is equal to this. So it is not, you are not supposed to cram it. It is not part of your hassle. It is given. Does your name has anything to do with the Chibira and the or the You are not the one. You are not the one who made the comment.
But still you will say worse.
Say worse. So this implies that these ones will go. Okay? These ones will be squared. So this would imply that ddx into sine squared theta then d capital theta, d small x will be equal to the constant, then multiplied by capital theta, implying that ddx from the trigonometrical derivatives from Pythagoras theorem, cos squared theta plus sin squared theta equal 1, so sin squared theta would be cos squared theta minus 1. So I saw 1 minus cos squared theta. So 1 minus cos squared theta the capital theta dx will be equal to, we bring the constant this side plus L plus 1 theta equals 2. So we have this is theta, this is the theta, and this gives us a differential, the first order differential equation. But all this came up when we said that the x was equal to cos theta. So then the equation, the radio equation, sorry, the angular equation, becomes, in the notes it says that the equation for theta, which is the angular equation. The angular equation becomes dx in 1 cos theta is x. So 1 minus x squared the capital theta dx plus L in L plus 1 capital theta equals to 0. Have I made any mistake? No. What is this called, Fred?
Angular equation.
It has become something. This was the angular equation, now it has become this. We no longer have angles, we have now x's. So this is called Legendre polynomials. This is called the Legendre's polynomials. Legendre polynomials, which are designated by PL theta, or if we put we can use the PX, not PL, PLX here, or we can substitute the x with the cos theta, PL cos theta. So now you have seen something which is religiously related to your mathematics. So this is Ix. Is that Ix or x? X. That is x, and this should be Ix. This is x. So we have the Legendre polynomials, and once we got the Legendre polynomials, yes. This one is. This one is okay. This one became square. This one is. This is 1 over sine theta times 1 minus sine. This is the minus plane, although this cancel. And when this one became squared, it is not minus minus square and then it goes, but remain with this minus which went with this. Hmm? This one here. It is friends with this. The theta was equal to minus sine theta dx. So wherever we with dx, we substituted with minus sine theta dx. Wherever we had a dx, after saying that x is equal to cos theta. Okay. Somehow. Mujumba will explain. You asked him and Mujumba knew, but he didn't want you to distract him. He knows his rights. He just knows his rights. So he knew that to start murmuring with you, you will take this time. So he said, I don't know. But in your free time, Mujumba will talk. So we have the general polynomials, and these LOs are the order of the polynomial. If it is 0, is there anything to power 0 is becoming 1, so it doesn't have any meaning. So you start from 1. Then you have the dx, like ddx. D squared, dx squared, orders keep going up like that. Okay? Chibira, you are putting the face like this, like things are not hard enough. May I know what is going on? So actually this is okay here. So the solutions of the general polynomials, which is PLX and OPL cos theta, since x is equal to cos theta, where L is an integer, representing the degree, of the polynomials. And from mathematics, or mathematical methods in physics, Legendre, is it Legendre like this or is it like this? This is wrong. Okay, so it is like this. So it is like this. Yes. So that makes this one wrong. I don't know whether he's German or I'm not German.
It depends, right?
On who is writing.
Yeah.
Okay. So, but I'm the same guy who wrote this and wrote this.
You are still right.
So Legendre polynomials are given by who gives them or who worked on them? Rodrigo. So are given by Rodrigo's. Some of you will call him Rodriguez. Rodrigo's formula. polynomial PLX can be given by 1/2 to the power L factorial d to the order n dxl, then x squared minus 1 to the power n. This is Rodrigo's, or some will say Rodriguez. Rodriguez is the formula. So we can substitute in LOs for the different for a couple of Legendre polynomials and see whether it comes out as it should be. But the generating function of this would look like I see you, some of you who have been doing part-timing in mathematics are seeing stars. And final. Don't have to be nice. Answer. You see that niceness is corruptive. You don't want to be beside, so you sweeten yourself. Yes, please.
I saw it coming.
You saw it coming. So they are generating function. Their generating function is B XR being the same as 1 minus 2XR plus R squared to the power minus a half, which is equal to summation L equal to 0 up to any of them, R to the L, then PLX. And we can write this generating function in a simpler way by introducing y equal to 2x r plus r squared, so that g xr equals to 1 minus y to the minus a half, and of course where the y we are introducing equals to 2xr minus r squared. If you substitute it to get back, and we can expand, and we write this where that is that, and expand using the binomial series. Using the binomial series, and once we do all this algebraic gymnastics, we will be able to get the first 5. You can get the rest of the polynomials. So the first 5. I normally write these figures to make sure that you don't get confused. You may see and write the first 5, but if there's a 5 in brackets, you know they're talking about the. Yes, please. Which one do we? This one here. This one here. This is right. Right. I write R like this.
Yeah, it is understandable.
That's how I write R, only that it slipped so down. But if you are uncomfortable, I write it like your R, the way you write it. I can defend myself. I even said right when I was talking. The good news, I'm on record. That's where, when I was going to say and expand, I said right. So we write this where that, then and expand in binomial series.
Yes.
So the first 5 polynomials are what have you written, Fred? No, this one. What have you written?
Wait.
Why?
I know.
You wrote why?
No?
Eh. Okay, so the first 5 ones, we generate them from Rodrigo's formula. So the first one is no, we don't start from 1, we start from 0. L equal to 0. So for L equal to 0, this would be P0x, which would equal to 1 over 2 to 0, which is 1. 0 factorial, 1. The 0 to this, does that make sense? And then this one, 1, so everything becomes 1. So this is equal to 1. The second one, L equal to 1, P1x equal to 1. Okay, we put 1 is a 2, 1 factorial is, and then here we differentiate, we put in 1, so we differentiate x squared minus 1. 2x minus 1. Or 2x. And then we divide by 2. Yes.
But where is 1 and where is the first derivative, the second derivative? Does also the zero derivative exist?
Any number 4 is 1.
Yeah, I'm not a mathematics teacher. I'm a physics teacher. I'm just borrowing mathematics. Ask your math people. So this will be equal to, this is equal to x. Then we got n equal to 2. So this is P2. And this would equal to, we put a 2. So you do that. And to avoid equations like this, I do my 5. So it comes half into 5x squared minus 3x. For n equal to 3, P3x equals to, no, this is supposed to be a half into 3x squared minus 1. And this one is the half 5x cubed minus 3x. Then we said the first 5, 1, 2, 3, 4. The fifth one is P4. So the P4 would equal to 1 over 8 in 35x to the 4 minus 30. This is what? 32 or 30?
32.
30x squared plus 3. You will find, if you find this 32, then we can. But I don't think I can write a 2 like that. My eyes are not good. But x is equal to cos theta. So do also for P1 for when it is cos theta, P2 release, and finish those also. They are on web. Page 58. Si muere nuts. Page 58.
This one on the first page.
Then we got the in this case of azimuthal similarity, in this case of azimuthal similarly, we just assumed azimuthal similarly, so this is not the ultimate solution of the fully fledged case of spherical similarly. So in this case of azimuthal similarly, in this case of azimuthal similarly, the separable solution to Laplace's equation is given by the other equation now looking nicer. So we'll have dr theta equaling to al r to the l plus bl. So a r to the l plus the b over r to the l plus 1. I think we need to have an l here. Combination of separable solutions. Yes, there is an l here and an l here. And then we have the notes, these are missing. It shouldn't be missing. So PL was there. The general solution, these are missing in the lines. The general solution to Laplace's equation then is taken as a linear combination, then is taken as a linear combination of these separable solutions. And these separable solutions where V equaling to separable as in radial and angular as being the same as R and theta. And once we have these two, we can now write our potential solution for the potential very confidently and say that therefore our VR theta is equal to, we sum up all of them. We sum up all the solutions, the linear combination of these solutions from L equal to 0 up to N, and then we have the AL, R to the L plus BL, R to the L plus 1, in PL cos theta. And this is our solution to give us the potential. This will be equation 11. Did we have 10? So there is an example in the 10 was it equation 10 was that one of the angular equation that resulted into on arranging that equation we got the Legendre polynomials. It is until when we do something, an example, that we'll be able to understand what we are doing. So this example is in Griffith. I don't know which page it is in Griffith. You can check it out. I don't have the textbook here. And this example exactly gives us the scenario of a field that would be having the azimuthal symmetry. And this is a case of the Earth. So assuming the Earth has a sphere. So, but before we go to the Earth, we say if we have a conducting sphere placed in an electric field, then this is what will happen. So, example. The text about the example says that a conducting sphere, the examples, if you realize in this course, we don't do examples because I don't like problems. They are not like a sphere is press this, find. Even when I was looking at the shell, I did not say a shell of charge this and then define. No? Just need to know the concept of what is going on. So a conducting sphere, we are looking at an example of a conducting sphere. A conducting sphere placed in a uniform electric field. So we are having an electric field which is vertical. And in this electric field, we are placing in there a conducting sphere. Okay? So let's see what happens once we have put it there. If it is facing upwards as we have made it here, definitely we shall have we know that the field is originating from positive here and going to negative. Okay? When that happens, it means that because the charges on the southern hemisphere of our sphere, the charges there are positive, so they would attract all the negatives towards the southern hemisphere. Then you would have the positives attracted to the northern, and definitely you won't have the external field where you put the conducting sphere. You wouldn't have them flowing freely inside the sphere. So we wouldn't have anything as a field inside the sphere. So I am rubbing this field here. It is not going to be anywhere. So we have this part here which is positively charged, and this one gets a negative charge. Okay. Now when that happens, then a field gets developed inside the sphere, and that stretches a little bit on the outside, and then it distorts the external field. So then you find that if these were to be the axes, on what? Where now, I am not going to draw, but now you have a field that is facing downwards in the sphere, from the positives that have been separated and the negatives that were separated. But this is not, it is not officially just constricted inside the sphere. It will also stretch a little bit of the outside of the sphere, around there. So it will start opposing this one, which was straight, which was comfortable. And then when that happens, if this is X and this is Y and this is Z, these are just drawing the axes. Of course, this goes minus Z. When that happens, then you get these being distorted now. So they do not come straight, but tend to kind of being distorted like this. Even this one now gets a little bit distorted. This one actually gets attracted towards. This was positive, these are negatives. So these were negatives up here. They start now sort of originating from where these positives are. And then this one, which is near here, gets a little bit pulled towards the sphere, then it goes down. Then some other one, which is far away, says, you fight with your problems, me, I'm okay. And goes straight. The same applies to this other side. So this one gets distorted and starts from the positives here and continues to complete the field line. This one also says, the other one was, these people blocked me, I can start from here. This one also said, going this way is laborious, let me start from this charge here. Then this one says, but you people are leaving me alone, how do I survive? That doesn't reach. And then if there is another one here, goes straight. And in the same scenario, these ones try to start from these negatives here. These ones go to terminate on these negatives here. A little bit of distortion, critical distortion, and then this one we have already. We placed a conducting sphere in an electric field. Now see how the electric field has been distorted by the sphere after it got some entanglement. You come here when you are innocent. When you get into a relationship, even to attend a lecture is a problem. You quarreled yesterday, you come here, you are wondering, should I sit in front of her or behind her, or aside? So you get distorted. Anyone here who has that problem? Where I am telling the truth. So I never got to experience that because I was broke. To me, I was concentrating on my books. Here, I suffered locally. So a conducting sphere placed in an electric field, I've now shown how it happens. So whatever I'm writing now is what I've already demonstrated and how it happens. So a conducting sphere, when it is placed in an electric field, these are a couple of things that happen. So an uncharged, so this is an example of a sphere placed in an electric field. So an uncharged, previous an uncharged conducting sphere of radius capital R. So if its radius was capital R, is placed in a uniform, electric field of intensity, E is equal to E naught K. So this is the reason why you saw me writing it facing this side. This is along the Z is K roof. This is J roof and this is X roof. Now, what happens when this case arrives is that the field will push positive charges. The field will push positive charges to the northern hemisphere. Is it northern hemisphere or northern surface? The northern surface of the sphere. Leaving the negative charge. Leaving the negative charge on the southern surface. So this example here is the one which has the most views on my lecture. Now it is 7.4 case. 7,400 people have viewed me chop this number. So this induced charge, this one here, this induced charge in turn distorts the field in the neighborhood. It's up to you. You can say neighbor in the British English or neighbor in the American English. The Americans don't put a U, the British put a U. Neighbor, B-O-U-R, labor, B-O-R for Americans, and B-O-U-R for the British. For Ugandans, you don't know. For Ugandans, you don't know. So distorts the field in the neighborhood of the sphere. In the neighborhood of the sphere. So I've already demonstrated that. I've showed you already how these bendings happen. So when that happens, we are supposed to find the potential, in the region outside the sphere. Our task in this example is to find the potential, the electric potential, to avoid people thinking it is some other potential. Let's be clear. Find the electric potential in the region outside the sphere. So you can now draw this diagram. And then we shall find the potential on money. Yes. Yes, please.
Yes, we will explain all this, how the field gets distorted, what, how are these, all the elements observed.
You can get a sphere, you put a plate, a positive plate this side and a positive plate this side, and put iron filings. And then you see iron filings making outlines. No, this is not magnetism, this is electricity. Hey, what do you use in electricity? Huh? Charges. What do you use to visualize this? Fine. You have some suggestion on how you can observe this? I will find out, see how you can. You want how you can visualize it, like an experiment where you can see this distortion happening. In the first year in electricity and magnetism, there was supposed to be an experiment where you can trace, where you can be able to trace the electric field lines, at least for I don't remember whether you had some circular whatever, so you keep, I don't remember how it's supposed to be done. But if you go in the manual for electricity and magnetism, you'll find that it's that experiment. And then we ran out of the carbon paper and whatever, the experiment got now for it. And this is African. We can spend a week without power. In a top university, in the Harvard of Africa. So things happen. If there are no other queries, you can chop it before we meet on Monday, and when we reach here, you say, can we go to the cylindrical coordinates? But we shall begin here on Monday, so that we are able to chop it properly, and then finally move on to the cylindrical. And then once we have finished cylindrical, we shall just try to solve for SOP using a vacuum diode. And then finally we go to the steady currents. Quickly wrap through steady currents, go to magnetostatics, and our goal is to make sure that we rush towards Maxwell's equation and then get the basis of telecommunication engineering. Enjoy your evening.